Hey everyone, welcome to our YouTube video, and in this video we are going to discuss a very important rule of the digital electronics, that is the De Morgan's theorem. Now De Morgan's theorem basically comprises of these two theorems, the proof of which we are going to see in this video. So we are going to discuss the De Morgan's theorem for the Boolean algebra and the digital electronics, and both these theorems will be proved in this video. So before I proceed, let me request you to please subscribe to this YouTube channel and share this video with your friends if you really like it. Alright, so the first theorem says that the complement of a product of variables is equal to the sum of the complements of the variables. And the second theorem says that the complement of a sum of variables is equal to the product of the complement of the variables. So technically what is happening here is that there is a situation where if we have two variables, that is x and y, then the product of the complement is equal to the sum of the complement, and complement of the sum is equal to the product of the complements. Now let us see the proof of this. So for example, the first rule says that x y bar is equal to x bar plus y bar. So technically what this is asking us to do is first focus on the left hand side. So on the left hand side, as you can see, we have product here. So for a product, the only gate available is the NAND gate. So let me draw a NAND gate, give it two different inputs, and let us see what is the output. So for a NAND gate, if the product is x and y, then the output would be xy bar. So this is the LHS part of the equation. Now let us see what happens in the right hand side. So in the right hand side, we need x bar and y bar. So let us take an input x, let us take an input y, and since we need x bar, so we first need an inverter gate. So let us apply an inverter gate onto this one. So now this gets converted into x bar and y bar. Now since we need an addition of this, so the only gate available is the OR gate. So let me add an OR logic gate and see what is the answer. So whenever you supply any input to the OR gate, it technically adds the product. So this is x bar plus y bar. So this is one part of the solution. So as you can see that x bar y bar here is translating. So this is the output of this particular logic gate, and this is the output of this particular logic gate. Now let us see what happens when we use a NOR gate. So in the NOR gate, what happens is that the input variables would be inverted on the input side itself. So now in this case, the output would be x bar plus y bar, and that technically is generating the same output. So I can write this as equal to x y bar. Now what is happening is the left hand side of the equation can be viewed as the output of the NAND gate whose inputs are x and y. On the other hand, the right hand side of the equation is the result of first inverting x and y and then putting them through an OR gate. Now these two representations are equivalent, as you can see in the figure. So this implies that an OR gate with inverter on each side, like right here, is equivalent to a NAND gate. Now when the OR gate is with inverted inputs is used to represent the NAND function, it is usually drawn in this kind of fashion, where the small circles or these bubbles represents kind of the inversion that we are looking for. Now in the second case, what is to be proved as a part of the second theorem is that x plus y bar is equal to x bar dot y bar. So as far as this theorem is concerned, you can see that on this side first we need x plus y whole bar. So technically what we are looking for is a NOR gate. So let us draw a NOR gate, give it input as x and y, and the output that we will get is x plus y whole bar. And if you want x bar dot y bar, so clearly what you first need is an input x and input y, and let us apply an inverter gate onto this side. So when we apply the inverter gate on this side, this becomes x bar and y bar, and let us now add an AND gate onto it, and then this would be equal to x bar dot y bar. So as you can clearly see that in this situation what is happening is that the influence of the gates is clearly visible. So if I take an input x, if I take an input y and substitute it with these circles and apply a NAND gate over here, then this is equal to x bar dot y bar. So this is equal to x plus y whole bar. So I hope that this proof of the De Morgan's theorem was useful enough, and please share this video with your friends if you really like it. For more such videos, don't forget to subscribe to this YouTube channel. Thank you so much for watching.